Ladies and gentlemen, greetings. I am Chen Wanjiang from the College of Computer Science and Software Engineering at Shenzhen University, China. Today, I am here to present on the topic of benchmarking the robustness of cross-view geolocalization models. First, let's introduce what cross-view geolocalization is. Imagine we have a query image in a ground view. We compare this image with geotagged aerial reference images from a top view to determine the spatial location of the query image within the geographical context. Commonly used datasets for cross-view geolocalization include CVUSA and CVACT. CVUSA is collected from the suburbs of the United States and contains a total of 44,416 pairs of ground aerial images. CVACT is collected from the suburbs of Australia and contains a total of 137,218 pairs of ground aerial images. It is worth noting that the ground images of these datasets are almost all collected in good weather conditions, so the ground query images are clean. However, in real-world applications of cross-view geolocalization, ground image corruption is ubiquitous, such as bad weather, sensor noise, etc. The figure shows a case where existing cross-view geolocalization models fail to locate when the ground query image is corrupted. This poses a significant challenge to applying this task to safety-critical applications such as autonomous driving. Therefore, it has become necessary to create an easy-to-use corruption robustness benchmark and comprehensively evaluate the robustness of existing models to corrupted data before deployment. The main contributions of this paper can be summarized as follows. First, to the best of our knowledge, we have benchmarked the robustness of state-of-the-art cross-view geolocalization models against real-world data corruption challenges for the first time. We have generated about 1.5 million corrupted images based on the CVUSA and CVACT datasets to establish benchmarks for assessing the robustness of cross-view geolocalization models. Second, based on the benchmark study, we have several new insights. One, in most cases, the clean performance or act clean of a model is positively, but not absolutely, correlated with its robustness. 2. Snow, spatter, and zoom blur more significantly affect the robustness of various models compared to other corruptions. 3. Models trained on more intricate scenarios, for example CVACT, exhibit better robustness. And finally, introducing stylization and histogram equalization as data augmentation techniques, along with our proposed training strategy, significantly enhances the robustness of various cross-view geolocalization models. The corruption of common ground images is mainly divided into 4 categories with 16 subcategories. The first category is weather-related corruption, which includes snow, frost, fog, brightness, and splash. The second category is blur-related corruption, including defocus, glass, motion, and zoom blur. The third major category involves noise-related corruptions, which cover Gaussian, shot, impulse, and speckle noise. Lastly, the fourth category includes digital corruptions, including contrast, pixelation, and JPEG corruption. To better simulate corruption in the real world, each type of corruption also contains 5 severity levels. We created to fine-grained corruption robustness benchmarks CVUSAC and CVACTC and 3 comprehensive corruption robustness benchmarks CVUSACL, CVACT_ValCL, and CVACT_TestCL from the classic cross-view geolocalization datasets CVUSA and CVACT. The figure shows visualizations of several common corruption types and severity. To enhance the robustness on existing models to corruption, we investigate the data augmentation methods, stylization, and histogram equalization. By applying stylization or histogram equalization to the training data and adopting our proposed training strategy, we effectively enhance the corruption robustness of multiple cross-view geolocalization models. The detailed information of the proposed damage robustness benchmark is shown in table. The evaluation metrics are shown in Formula 1 and Formula 2. Next, we introduce our benchmark test results. The experimental results of 8 cross-view geolocalization methods on the CVUSAC benchmark are shown in the above table. The experimental results of 7 cross-view geolocalization methods on the CVACT_ValC benchmark are shown in the following table. The relative corruption error RCE results of different cross-view geolocalization models on the CVUSAC and CVACT_VALC benchmarks are shown in the figure. According to these experimental results we can find 1. In most cases, the cleaning performance of a model is positively correlated with its robustness, but not absolutely. 2. Compared with other corruptions, no, splash, and scaling blur are more susceptible to variance. The impact on model robustness is more significant. 3. Models trained in more complex scenarios such as CVACT show better robustness. Stylization improves the robustness of SAFA, L2LTR, and Transgeo on the CVUSAC benchmark. CLAHE improves the robustness of SAFA, L2LTR, and Transgeo on the CVUSAC benchmark. Our further discussion of this work includes real-world corruption complexity. Real-world corruptions are extensive and complex, and not all can be enumerated. Design corruptions, 16 corruption types, each with 5 severity levels, were systematically designed to generate rich data for research. Synthetic imagery advantages. Synthetic images offer controllable and diverse data by adjusting conditions like weather and scene types, providing safer and more ethical research alternatives. Practical testbed. The benchmarks created serve as a practical testbed for evaluating the robustness of cross-view geolocalization models. Broad applicability. While focused on cross-view geolocalization, these robustness benchmarks are applicable to other research areas like cross-view image synthesis, camera pose estimation, and autonomous driving. Finally, our work is summarized. This paper systematically investigates the impact of corruption data on cross-view geolocalization models, which is a challenge previously overlooked in the context of cross-view geolocalization studies. We propose to fine-grained corruption robustness benchmarks CVUSAC and CVACT_VALC and 3 comprehensive corruption robustness benchmarks CVUSAC, CVACT_VALC, and CVACT_TEST for the cross-view geolocalization. Extensive experiments are conducted to evaluate existing classical methods on these corruption robustness benchmarks, revealing new insights. Furthermore, we introduce to simple technique stylization and histogram equalization and the training strategy to effectively enhance robustness. Thank you. This is the end of my speech. Welcome to visit our project homepage. The project provides my benchmark download link and related code. If you have any questions, please contact me by email.